Hello, good morning, everyone. So let's start our third day. So it's nice that you still have some people, but I would like to have more. I see that there are someone arriving. Thanks, Dalber. So the morning section, we are going to start with another invited speakers, Professor Waldemar Macedo from CDTN, Minas Gerais. He's going to speak about application of Musball spectroscopy and nanomagnetism. Professor Waldemar, please.
Okay, Edson, thank you very much for the invitation and to give me the opportunity to be here. And I will talk about application of Musball spectroscopy in nanomagnetism. I will try to complement a little bit what Jean-Marc has shown to us yesterday. And I will, let's say, concentrate in thin films, okay? And just to show you, this is in fact, my institute is inside the university campus in Belo Horizonte. We started with this small reactor. This is the beginning of the institute, and now we have a big campus. And we're just close to the physics and the chemistry departments at the FMG campus. And we are like an island inside the university campus. And we are very close to this is the stadium in Belo Horizonte. And my lab is this is the top, where the low part of the campus and the high part. And of course, we have to be at the top. This is where my lab is. Okay, and okay, what we have there is a lot of facilities for sample preparations of, okay, under very controlled conditions. And we have surface science systems and growth chambers. And we concentrate for what is concerned with Musball spectroscopy. We can prepare samples by molecular beam epoxy, and we can combine in situ growth and characterization for many techniques, and we can play with iron isotopes, okay? And also by sputtering, okay? This is why not very common, okay? And, okay, and we have all the standards characterizations, and what is, let's say, not very common, we can do SEMs at low temperature in a very small vacuum chamber that goes inside a cryostat, and we can do Musball spectroscopy, let's say, to a very low amount of iron-57 with a very small homemade detector. Okay, and as I said, Jean-Marc was talking about these things, okay, and more about nanoparticles, and we will concentrate on layered nanostructures based on iron, and I will say a few words about depth selectivity. I was expecting to talk before Kai, but the program has changed. But anyway, for the students, I will say a few words about depth selectivity and show some examples of applications, okay? I don't know how far can I go, but we'll try to show some examples. Okay, we all know that, okay, if we can detect with Musball spectroscopy, you have different phenomena going on, and we can detect electrons, X-rays, or gamma rays after the absorption, and we know that conventional electron is surface sensitive, okay? And if the sample is not homogeneous, we can see different spectra. But in fact, we have a lot of processes following the absorption of a gamma ray, and we have a lot of electrons emitted in these processes. And what we can say is that if we do, of course, the electrons, they lose energy when they are moving to go out of the solid. And if we do, let's say, integral detection for electrons, depending on the electrons that we detect, okay, we can go deep in the solid, but let's say around 10,000 angstroms for K electrons, and up to 3,000 angstroms if you detect even the early conversion electrons, okay? And if you use an analyzer to, let's say, to select part of this energy spectrum, we can get by using an energy analyzer what we call depth selective conversion electron Mossbauer spectroscopy. We, due to the process of energy loss, we can have not more than 100 angstroms depth resolution, okay, in this way. That means it's not very nano sensitive. But what we can do if you want to have a really nano resolution is we can play with the isotopes when we prepare our samples, as Kai has shown to us on Monday. Okay, then we can have a resolution of, let's say, the monolayer regime, okay, and you can be surface sensitive, very surface sensitive, but you can go also to very buried interface. That means you can go up to 3,000 angstroms deep, okay? That is really very effective for magnetic thin films and multi-layers, okay? And this is really very powerful because you don't have many techniques that can do that, okay? But for example, if you apply XMCD, magnetic dichroism for X-ray absorption, you can be element selective, okay, element specific, but you don't have a big depth resolution. That means you cannot go to deeper than, let's say, 440 angstroms, like something like that. That means it's really only is limited the depth selectivity of X-ray absorption, okay? But if you play with isotopes, you can go, you can have a resolution in the monolayer regime, especially if you use synchrotron, and you can go really deep in the structures with that. This is a very interesting approach, okay? What we do in our lab is, okay, we try to correlate structural magnetism in many systems, nanoparticles, multi-layers, and so on. But you concentrate today in this kind of structure grown by taxi or by sputtering. And what we do is always, when possible, when we have iron, we try to use iron 57 probe layers. And also we try to use, when possible, when we get beam time, synchrotron techniques as complementary techniques to characterize nano systems, okay? Just to finish the discussion, to complement what Jean-Marc said yesterday, one thing that I didn't see here, I was expecting to see, we had a lot of works on nanoparticles, okay, is that I see that the community is not using synchrotron that much. For example, XAF. So I didn't see any work with XAF. I just put this is a work we did long ago in the beginning of our synchrotron, okay, by combining XAF and Mossbauer, for example. This is a very powerful approach, okay, and we should do that, okay? This really we have here in the Latin American community should use more synchrotron, okay? This is just to stimulate you to apply and to use to complement. Is a very complementary approach, okay, using the X-ray absorption and Mossbauer spectroscopy, especially for nano, okay? And again, about the talk from yesterday, this is another work on nanoparticles. There was a work led by Josep Nogués from Barcelona, trying to understand the iron oxide nanoparticles. We had, in this work, we have a multi-technique approach using neutrons and so on, many techniques. And it took us 4 years to understand the system, okay? We worked 4 years in many people, many techniques to understand iron oxide nanoparticles. So this is not that easy many times, okay? Okay, just to say something about what was the discussion yesterday. Okay, what I want to show you is some works on on exchange bias systems, interdiffusion at interface, and also magnetic anisotropy on thin films. And if the Sherman allows, I will show an example from synchrotron and work from the Mitsui in the Spring 8 that I think is very interesting to me for personal reasons, okay? This kind of work we have been done was very important many years ago, and it still remains very important. For you see that the interface-induced phenomena in magnetism are very important for many aspects I will not discuss here, and also the coupling with antiferromagnetic materials. I'll say that we are going to the antiferromagnetic-based spintronics, and even in this case, you have many, let's say, Big Macs of magnetic material that are still very important for new device. Okay, and in this device, even for new device based on antiferromagnetic systems, the exchange bias effect plays a very important role. Okay, even nowadays, and it is not fully understood after 70 years. Okay, of the discovery of exchange bias. Okay, and that is just to prove that it's really important. These things are very important. There are some description of the topics from the MMM conference that was finished last week. And I was in the program committee of Spintronics. I was not there, but I worked a lot with these things. And all these aspects I was pointing are still very, very important, getting more and more important for, let's say, devices and new technologies, okay? Okay, let's go to, let's say, exchange bias systems. We started studying many years ago iron, manganese, and iron fluorides bilayers. There are model systems for exchange bias. And then we applied, okay, iron 57 probe layers with this. We have grown samples with these fluorides. And the important point is that these fluorides are ordered antiferromagnetic order, happens only at low temperature, below 70 K, let's say. Okay? And then we have grown samples putting the iron 57, 1 nanometer of iron 57 at different positions in these things, and we have measured in remanence in the standard SEMS. Okay? And as you show, we can see here, we have for this spectrum two things. First, we see that this iron, alpha iron spectrum is, you have this more contribution is the interface. Okay, it's very small. That means we have a very sharp interface in the system, and we see that from the intensity of the intensity of the lines, we see that we have here fully in plane magnetized sample. Okay, and that means if you want to see some effect in the spins due to the coupling at the interface, you have to go to non-perpendicular measurements. Okay, they have to go what we call SEMS in a non-perpendicular geometry. That means because if you have the spins rotating in the sample plane, by measuring like this, you see that the angle between the gamma rays and the iron magnetic moment will change. That means then you are sensitive to change in the intensity of the lines. Okay. This is what we did, and you can see that if you, as soon as you go down with the temperature, okay, you get the antiferromagnetic order, and you see the change in the lines intensity. That means you really see that even in remanence, the coupling at the interface causes a change of the spins, of the iron spins in the plane. And you see also that the change is bigger at the interface, okay? This is what we did in the beginning. And then, but we wanted to see what happens really during the magnetization reversal. And then we got the beam time at the synchrotron in Grenoble, in the ID18. And then we have prepared a sample that with, in Belo Horizonte, a sample with wedge of iron 57, this is iron 56, and then with 1 nanometer of iron 57 like this, okay? And then we see also that this sample has a change bias, were very well characterized. We see that the interface is sharp. We see here let's say the integral SEM spectrum. And then we went to Grenoble, where we can, let's say, you can explore that the small size of the beam, synchrotron beam, and we can mounting the sample inside of the eukaryote. You can, let's say, we have a table with a micromotor. You can, that's in this eukaryote with moves in front of the beam. That means you can make spectra. You can take spectrum at different positions of the sample. That means a different distance from the interface. That is what the idea. Okay, and that means for a standard SEM spectrum, you need 1 week, and for in synchrotron there, we need, let's say, 1 hour for a spectrum, okay? In a very small region. And then we can, okay, from the spectrum, we can see, okay, we can calculate the orientation, the average orientation of the spins, and this is what we did. This is the team at that time. You can see this guy is sitting there, okay, a little bit older, but he was doing his PhD at that time, and we shared the beam time with them. Okay, was that very good beam time, nice time. And Ralph Rosberger, and Balaram, and Olaf Leopold, and Johannes Heisemenger is now in Zeiss. Okay, but we took the spectra, okay, along with the applying field that we did a hysteresis loop, okay. And what we got was that we see that when we at different positions of the sample, you see that we see a shift in the loop. That means we see that we have a pinning, stronger pinning at closer to the interface than away. And you see also that with the spin rotation is by formation of part domain walls in the ferromagnetic layer. That means some like spring magnet, what you see here, okay? But we are not able to complete the experiment due to the beam time, due to Kai. He was losing part of the time for his PhD in another kind of samples. But the very important thing, at that time, we were not able to understand the spectra at the very interface. Do you remember that, Kai? Okay, up to now, we don't know how to handle with the spectra we got at the very interface. Okay, but then we want to complete that kind of work, and without a synchrotron, okay? How could you do that, okay? And we tried to do at home, doing standard SEMs, okay? Then we choose another antiferromagnetic. There was a iron manganese that is ordered at room temperature, okay? That is what we did in our lab. To see, many of the theory on exchange bias, they consider the ferromagnet layer as a single big spin, okay? They do not consider asymmetry in the reversal of the magnetization, okay? And then what we did is that we used our sputtering system to grow samples with iron 57 at different positions. No? It took us years to be able to get samples that are really compatible by playing with the iron 57, because you grow iron 57 by evaporation inside the sputtering. That means to have samples that are really equivalent of the samples that are fully grown by sputtering. Okay, this was a big task, but we finally succeeded, and then we have samples that are really very similar from the magnetic point of view, and then by doing this more, again, we do SEMs, we see that they are fully in plane magnetized. We see that the intershapes are very sharp. Okay? If you have the iron 57 in the center of the sample, you see only alpha iron spectrum, okay, for example. And then we can, let's say, go to the non-perpendicular geometry. You can do Mosel spectra by applying an external field, and you can measure many spectra. You are sensitive to in-plane rotation, okay? This is what we did. You can follow the spectra, and you see that by taking the line intensity ratio, the R23 from the different spectra, you can construct a semi-angular loop, like we did with the synchrotron from the NRS nuclear resonance scattering spectra, and then you are sensitive to, you can see the iron spin rotation in your sample by Mossbauer. Okay, then if we compare the Mossbauer loop with the vibratory sample magnetometry loop, you will see that they are different, because the blue one is an average, okay, and the red one is depth selective, okay. Then you see that, for example, here, you see that the top layer rotates, is easier to rotate than the average. Of course, the top layer is far away from the interface, is less pinned by the interface, okay? And if you compare then the three spectra, you see that the interface is more pinned, the center represents the average, and the top layer is less pinned, okay? And more than that, we see that the reversal here, if you go from positive field to negative field of this branch, you have one kind of rotation. You will have a formation of domain walls parallel to the sample plane, but you see that when you go back from negative to positive, if you do this way, they are all equal. They are all similar. That means the reversal is by equivalent rotation. That means it's a clear sign of asymmetrical reversal. And this is a kind of the thing that is not considered in the theory. That means they are really relevant for the improvement of the models, theoretical models for exchange bias, okay? Okay, let's say a few words about interdiffusion in this thing, okay? And cobalt, iron, manganese is a standard exchange bias system even for the industry. And we want to see how sharp is the interface, because you have to apply annealing under magnetic field to, let's say, to improve the coupling in this system, okay? And the idea was to see how sharp is the interface. What happens when you go do heat treatment in this sample, okay? And we did the same. We have ground samples by sputtering, putting iron 57, 1 nanometer at different positions. And we did let's say, the magnetic annealing at different temperatures. And what we see by Mossbauer is that starting from, let's say, 350 degrees, we start to see interdiffusion in the samples, okay? And we start to kill the magnetic signal. And at 500 degrees, we have a strong interdiffusion, very low, very few ferromagnetic phase remains. Okay. Oops. And if you look at the exchange bias, despite this big interdiffusion, we see that the exchange bias is maximum at 450 centigrade, what is really interesting. And you see that you have a maximum exchange bias, even you have a very strong interdiffusion interface, what is really was not expecting, okay? And we did also XPS. If you compare the samples with the probe layers at different positions, let's say the interface and 2 nanometers away from the interface, we see that interdiffusion is already 30% bigger at the interface than, let's say, 20 angstroms above, okay? And another interesting is that if you do XPS on top of this stack, you see that manganese, this is the biggest interdiffusion, manganese goes all the way through the stack up to the interface. Okay? You'll see that if you measure here, you see a lot of manganese after annealing, okay? But no interdiffusion this is the manganese that is the guy that is diffusing through the sample. And if there's something happens here, but if you compare with other results for the similar systems, you see that they have different results. They see interdiffusion much earlier with lower temperature. That means this kind of system depends very much on the processing parameters. Okay, that is very hard to compare results for different processing parameters. Another system that we were looking at for interdiffusion is cobalt iron. This is a new antiferromagnetic material. Okay, magnetic gold was discovered by Givor and co-workers in 2013. And because of the spin structure, you can have two in plane. If you take this material in this direction, you see that you can have in plane or out of plane magnetization very easily. That you have two different. This is very interesting material for spintronics, for example. Okay. And because of this different spin configurations that we see small energy barrier. And then we started in collaboration with Dominique Givor and Victoria Barton to grow manganese to gold thin films. And then we succeeded to grow this kind of films by sputtering. And the only way to try to see if you have really antiferromagnetic manganese to gold was to put a ferromagnetic layer and see if you get exchange bias, okay? And we did that, and we see that we get some, after annealing at 500 degrees, you get a small exchange bias. And we did also, and to see what happens at the interface after the annealing at this temperature, we did also Mossbauer by putting 1 nanometer of iron 57 at the interface between these two materials. And then we see that we have a really very flat interface, so only after starting from 450 degrees, we start to see a change in the spectrum, okay? That means this is the temperature where we start to see interdiffusion at the interface, but if you compare with the system with iridium manganese that is standard antiferro for applications, we see this guy is much more resistant to the diffusion than iridium manganese. We didn't publish this yet, but these are interesting results. At that time, I was away from the lab in the head in the institute, and it remains in the to be published. But we did some works with collaboration with a group from Sérgio Rezende in Recife, and we have shown magnons in these guys, and then it started to appear a lot of papers showing that this guy is really very interesting for spintronics. And Dominique Givor we did a paper that we submitted. This paper was not accepted, but this was, and I think that the editor didn't understand the importance of this work, but we didn't publish. This is really my, was a great pleasure to work with Dominique, really a great guy. Okay, but we recently we start to work again with the system with a master student. We playing with the thickness of the antiferro. Before we were using antiferro with 20 nanometers. Now we went down up to 2 nanometers, and we see that we get the same exchange bias doing the same kind of treatment. That means it's a little bit small, very disappointing, but we see that what we get is very much the same that the German group got recently with the same material, but in another orientation, the 001. Here we have a 110, but the exchange bias at 80K is very much the same. That means you are not far away from what the guys are getting today with this material. But that's to show that it's really interesting. This is a Nature paper, recent paper, and we see that they use the PIM to look at the interface between manganese to gold 001 and the permalloy, and they claim they have this very sharp interface, okay? And I really now we want to play just one mono. It would be very nice to put one monolayer iron 57, a very small layer of iron 57, and look at again at this interface. We are trying to do that right now. Okay. Okay. A few words about magnetic anisotropy. One way to get perpendicular anisotropy, for example, iron cobalt is a very important guy for magnetic anisotropy, perpendicular magnetic anisotropy. And the way to do that is to get tetragonal distortion by growing by epoxy in different substrates. And this is a model system, iron cobalt on rhodium. You have a big distortion, a C over A of 1.24. And if you grow iron cobalt on rhodium, you see that you're doing by Moch, you will see that up to 50 monolayers, you have a polar Moch, you have a square polar loop. That means you have perpendicular spins. But Moch makes an average, okay? They want to see what happens really along these 15 monolayers by using iron 57 probe layers. We did that years ago by growing always 12 monolayers of iron cobalt by co-deposition, okay, and putting always 4 monolayers of iron cobalt at different positions of these stacks. The important thing is that you have to know the sample you have, okay? Of course, doing by MBE, you have to know that you have a really good epitaxial growth, that the composition is really chiatomic by doing, for example, Auger spectroscopy in situ, and then you do Mock in situ, you see that the longitudinal Mock loop is not square. That means the moments are not in plane, it's out of a plane, or there is some perpendicular anisotropy. And then we did the SEMS, okay? What we see is that at the very interface, you have the blue one is the spectrum of the iron cobalt, and the green one is the interface. What we see is that, let's go quick with that. What we see is that at the very interface, you see really, really fully perpendicular spectra, okay? But as soon as you go 4 millimeters away from the interface, we start to see some canting, okay? Let's say we represent by with equivalent to 30 degrees out of canting, but why? How can we explain that? Well, I think that the explanation is that it means this guys has shown that for iron, cobalt, and rhodium, starting from 4 monolayers, we start to have the growth changes from 2D to 3D. That the island that starts to appear, that this can explain this canting, okay? This is, okay, what we expect, we suppose explains this canting that starts to appear when you look by Mossbauer for monolayers away from the interface. Okay, but not only tetragonal distortion can contribute to the perpendicular magnetoanisotropy. There is a theoretical work, recent theoretical work, that is the chemical order can also contribute. It's a very important, okay, for perpendicular magnetoanisotropy. And they propose that the copper 3 gold, or this lattice parameter, will be very, very important to get. If you get this parameter, this distortion, okay, and plus this chemical order, you could get perpendicular anisotropy in iron cobalt. And that is, and the only experimental results we had at that time was this work. They have grown this kind of material, okay, 1 monolayer of alternate iron cobalt monolayers, but they measured the magnetism only for 11 monolayers, and they saw in-plane magnetization. And they speculate that by Reed gives you a measurement of the structure of the sample, they saw some change in the structure of the sample at 10 monolayers that claim that, okay, we did the magnetic measurements here after this transition. That means if you are here, we should see perpendicular anisotropy. And this is what we decided to see, to look at, okay? To grow iron cobalt alternate monolayers on copper 3 gold below 10 monolayers, okay? Then we have investigate the growth. You have very nice epitaxial growth, layer by layer, okay? And we went up to 7 monolayers. And this is the Mossbauer spectrum for a sample with 7 monolayers iron cobalt, okay? What we saw is that this was a very rough measurement, but we saw that if you grow by co-deposition on rhodium, we see that we have perpendicular spins. But if you do the same in copper 3 gold, by co-deposition, we see in-plane spins, but if you alternate, okay, if you do some chemical order, we see a clear change in the spins, okay? We are not able to do 1 monolayer iron 57 Mossbauer spectrum in situ because of the time of measurement. It does not make sense in our system. And then we decided to go, we see that chemical order matters for this system, but we cannot do by Mossbauer. Then what we did is by Moog. Okay? What we see here by Moog is that every time we say one monolayer iron, one cobalt, one iron, cobalt, we see that every time you grow one monolayer, you will see that the spins change. Okay? You will see that the spins are changing from in plane to in plane every one monolayer iron cobalt. Okay? If you put alternate monolayers. And if you do the same by co-deposition, you see always in plane spins. Okay? This is a very interesting system, very delicate. The magnetic isotropy is very delicate balance in the system, but we see then that the chemical order matters for the anisotropy in this system, but the one monolayer resolved in Mossbauer investigation is still missing. Okay? And what we did to try to understand more this system, we went to the synchrotron. Okay? And what we did is XMCD. Okay? Then what you can do? You can do element specific. We can measure the magnetism in the different board edge, iron, cobalt, and also we did in the copper edge. And we saw also dichroism in the copper. That means copper is magnetic in this material. Okay? Okay, we can do element specific, but not depth resolved. This is the point. Okay, it is a complementary, but you do not get any depth resolution in these measurements. Okay. We did okay. We calculated the moments and so on. That means we cooperate with the theoreticians from Campinas, and we are able to grow the, let's say, the epitaxial growth, theoretical growth. We got all these numbers, but the important thing is that only from the calculations we could show that in copper, for example, the magnetism happens only at the very interface, because the copper 3 gold has an interface. The first layer is always a layer that has 50% copper, 50% gold. Okay, this is the order material, and then the calculations has indicated that only the magnetism have seen by XMCD is due to only the copper atoms that are in the very interface. That means the signal is from half a monolayer magnetic copper at the very interface. Okay? Okay, just to finish, I want to show you this example. This is a work from Takaya Mitsui from Spring 8 in Japan. And you see that this is a prediction of Friedel oscillations at the surface of iron 1 surface, okay? And that was predicted 40 years ago, and only recently they are able to prove that. These are what is this Friedel oscillation? That means that due to the, let's say, spin density in the system, if you have a free layer, you should expect increase in the magnetic moment of the iron, or variation along the first layers, but also a decrease in the hyperfine field, the oscillation of the hyperfine field in the first layers of this single crystal. Okay, and these are slides from Takaya's presentation at the LACAME' last year, and he sent me his presentation. These are slides from his presentation, and he has shown in his presentation there was an attempt to measure this done by Kiauka, and in fact, Kiauka was sharing with me this same system, the ultra-vacuum system for depth-selective Mossbauer spectroscopy in Duisburg. We both were sharing this system at that time, okay? And he was trying to see this effect, and I was trying to see what happens with iron, FCC iron expanded by, okay? And you see that this is the spectrum that Kiauka took at that time. That means this is simulation that since he has measured 30 ergs from iron 57, and this is the simulation. That means that would be oscillation. He should see these shoulders in the spectrum, and he didn't see, okay? But the measurement was done perhaps in a week or weeks, okay, in ultra-high vacuum. That means the surface was contaminated by rest gas, even in ultra-high vacuum. That means, now what they did in the spring weight, Mitsuo did this with synchronous Bauer. In synchronous, he was able to grow, let's put this way, this side. He was able to grow one monolayer iron 57 in iron 56, okay, and was able to, let's say, to see the spectrum from the very surface, or to resolve the Mossbauer spectrum layer by layer, one monolayer resolution. And you could see that at the interface you have a decrease of the hyperfine field. At the second layer you have an increase, and so on. And starting from the fourth layer below the surface, you have bulk-like properties, okay? And this is, okay, then they are able to do atomic layer, resolve the Mossbauer parameters in the system. It was a very nice work, okay? And it's very nice work also. As a lot of great work that you have seen already from Kay yesterday, from Monday, from his presentation. But I want to summarize here that is always very difficult. The correlation between structure and magnetism in nanostructures is very complex, as Jean-Marc said yesterday. And it's always, we wanted to have always a multi-technique approach. Is the best way to understand the system. And if you apply Mossbauer spectroscopy and the iron 57 probe layers, can help a lot many times. And we hope, and this is the message, I would recommend the Mossbauer community here to get involved in synchrotron, because we hope to be able to do something like that at home in the next years, okay? And we have a big expectative with what will happen at Sirius with that, in this regarding Mossbauer spectroscopy. And just let me show you, this is from Narciso. He sent me this slide last week. They plan for the second phase of the Sirius. They are still struggling to finish the first phase, and this government has made their lives really tough, okay? But they are planning for the second phase a synchrotron, okay, a Siriema beamline for resonant inelastic scattering. And what they are planning to have inelastic ray scattering plus nuclear resonance scattering, okay? And I will not give more details, but this is the plan, to have a line that can cover all these things with high resolution, very high intensity, high flux, okay? With that, I will skip that. Due to the pandemic, we stopped this kind of work. We are only working on nanoparticles. It was final comment. My student was working last year in getting cobalt-2 iron gallium Heusler nanowires, okay? Our idea was just to get nanowires to use them to do physics in a single nanowire, because cobalt, these Heusler alloy are 100% spin polarized in theory, okay? That means he wanted to have it very interesting for a spintronics device. He wanted to use a recipe that is in literature to get nanowires and use the nanowires to do physics. But using what you have in the literature, by using the chemical route, supported by SBA 15 silica, mesoporous silica. This is the way, okay, you use this structure to get nanowires, and then you get rid of the silica by dissolving the silica chemically, and you get your material. And people say that this works. You get pure cobalt-2 gallium with, okay, and you apply this recipe out, we see that you have a lot of iron together. And why do people say that? Because if you use only X-rays, you cannot distinguish, okay? This is a fit using the same spectrum, the same diffractogram, using only cobalt-2 gold, cobalt-2 iron gallium. And having 50% oil on 57, you see? It's more or less the same. That means if you don't do Mosbauer, be aware, be careful, okay? The message is that, be careful if you see works on Heuser alloys without good Mosbauer spectroscopy, okay? Okay, with that, thank you very much, muchas gracias, and I want to thank you, my collaborators, and you all for the attention, okay?
Okay, Waldemar, thank you very much for your nice talk, and also it has covered a gap that Gianmarco was not able to speak about. Now it's time for questions.
Let me just finish, Edson. Thank you. To say that my group is disappearing. Right? This is my group. Years ago, then it was, I think it was 4 years ago. But now I can say this guy went is in Germany. She is in Spain. He is in Vitoria. He is in the physics department. Okay. Okay, anyway, thank you.
Yeah. So, questions? Ja.
So thank you for this nice talk. What about the thickness exactly? Because you mentioned a thickness of 1 nanometer. So you are expecting to deposit a thickness of 1 nanometer. But what is really the thickness? Is there any roughness? Is there any extension of this 1 nanometer?
Okay, the thickness is always nominal thickness because, okay, that means if your film is really flat, you'll be 1 nanometer, okay? But what we do is we do reflectivity. We measure the roughness at the interface by X-rays and also by AFM if you have, okay? We know the roughness, okay? But you can estimate from the Mosbauer spectral source, okay?
On the one you are discussing on...
But just want to complement. From the epitaxial systems, we know that the roughness is really the spectrum of the interface corresponds just to one monolayer. That means the interface is very sharp. That is what we expect. Okay, if you have just one very sharp interface.
Okay, good. In the to interpret the hysteresis loops,
yeah.
What about the role of the demagnetizing field?
Okay, what we said, what we did is we measured the magnetic viscosity. Okay, to know that we can do this Mosbauer spectrum in a long time without any problem. Okay.
Roberto?
Thank you, Waldemar, for the nice talk, and I have a question. Could you come back to that system that you showed there is a kind of diffusion at the 500K?
Where is?
It's iron cobalt. I think.
Yeah.
Yeah.
Here? No.
No, more. No.
No,
Yeah.
it's okay. It's okay.
Yeah,
the question is because in my experience, generally we have verified that there is no diffusion, no strong diffusion up to 460 in 3D elements generally.
It depends how do you prepare. It depends on the quality of your sample. Depends how do you prepare. That means what we see is that we cannot. Are two things that are very hard to compare. First one is temperature in your sample, in these preparation systems, because it depends very much where is your thermocouple is, okay? And then be careful by comparing temperature of gross temperature and measurement temperature in these things, because it depends very much on your system. Your 500 can be very different from my 500.
Okay, understood. Because I said the behavior that you improve the exchange bytes up to 406, I mean.
This?
Like the, yeah.
Yeah.
And after that, you have another behavior.
You are really killing completely the magnetic phase. Okay, because
Yeah,
this is
that's
the magnetic measurement. But you see that the loop is the amount of magnetic material is decreasing a lot. Okay. You see the size, okay, the amplitude of.
But it seems to be what you said. So
Yeah.
Yes.
when you go down,
Yeah.
when you
Yes,
go
yes,
up,
like
up
that.
to 450, for example, you have an improvement of the
Yeah.
exchange bias.
Exchange bias
And then if you go
is
further
growing. The
in
Yeah.
exchange bias is growing. It's negative, but it's growing. Okay,
Yeah.
it's
No,
bigger and
I
bigger.
know, I know.
and that's-
Okay.
No, because you said that there is a diffusion.
Yeah,
in
but
the
if you look
temperature.
at Mossbauer, is this the spectra are here the same? Okay,
But the diffusion starts at what's the
350.
350.
Okay, you have to see start to see diffusion here, but
Yeah.
okay, here you almost kill the magnetic phase, but the exchange bias is there, is the maximum actually.
Yeah.
Okay, the remaining material is coupled. Okay,
Okay,
we have time for one more question.
we can discuss later. But
Yeah, it's better. One more question. If not, I'm going to make. Can you show the first system that you have? So you have done some two spectra. You got two spectra at two different temperatures.
which one do you mean?
The first system, it's iron on, if I remember, manganese fluoride.
This one.
This one.
Yeah.
So when you go to low temperature or high temperature, I don't see from now. So you have changed the 2 and 3 lines, and you assume completely this effect due to the coupling between the iron spin. My question is, when you do the temperature dependency, you have also internal strain that increase. So did you
No,
take
there's
into
nothing to
account
do.
this?
This is I took away a slide. What we see is that, let me come back. What we see is that the spins are in plane. Okay,
Okay.
we apply the field in this direction. Okay, and you see as soon as the coupling, the spins in the antiferromagnetic layer are pointing in this direction. They are quasi. The spins are at the interface in the antiferro are pointing in this or in that direction.
Okay.
That means the iron, the ferromagnetic iron
So it means
layer is couples within these two directions. This is why.
You did not expect a huge change in the strain due to the
No,
temperature
no,
difference.
this is
Great.
just because
Okay,
you
thank
can go up.
Okay.
You can just few degrees. If you
Okay.
below or
And then
above the narrow temperature of
okay.
the ferromagnet.
Okay.
This is due
That's
to
clear.
this is clearly this spins pattern is printed in the
Okay,
in the
thanks.
ferromagnetic layer.
I didn't
okay?
catch this.
Yeah,
Thank you.
I took on a slide that
Okay,
would show that.
thank you.
Okay.
Okay, let's thank the speaker again. So the next talk will be Renzo Rueda. It's here. So Renzo is going to talk about Mossbauer's study of core single shell and core double shell polymer functionalized magnet.
Well, good morning, everybody. Thanks, Professor Pasquevich, for the presentation. My name is Renzo Rueda. This study, entitled Mossbauer study for the core single shell and core double shell polymer functionalized magnetic nanoparticles, we start the proposal to produce nanomaterials biocompatible, and that present and promote an improvement in their physical properties. But how does this work? Before explaining what we have achieved, I will give a brief introduction to this. Well, the accumulation of waste, industrial waste, water, and contribution to pollution, water bodies, are reducing the sources of water that serve as ecosystem for biological organisms. Give this nanotechnology for alternative to face his problem. Mainly in the research group in San Marcos, Peru, Nanotech. We have we take nanomaterials based on iron oxide, biocompatible for use, and nanoremediation have been produced. That is ecotoxicity studies with from here, Daphnia magnas, where we calculate LC50 for ecotoxicity, and ton. So we synthesize nanoparticles with functionalized with polymers, but constitute the core of the magnetic core. Yeah, the polymer principal in this work is polyacrylonitrile, and polyaniline. So this work we see the improve the physical properties of the gamma phase of iron oxide, known as maghemite. For the synthesis of maghemite with functionalized with polyacrylonitrile, we start with synthesis of the sample of use the chemical co-precipitation route was followed. Then for the first sample, the salt of iron 2 and iron 3, iron sulfate and iron chloride were used in molar ratio of 1:2. This is the combination of the salts of the iron 3 and iron 2, chloride oxide and sulfate oxide, iron oxide. We were 500 milligrams of the polymer, polyacrylonitrile. Of the polymer we use and dissolve in 200 millimeters of distilled water. It was stored at 50 RPM at 80 centigrade for approximately 30 minutes. During agitation, small lumps form that were dispersed with an increase in revolution in agitation. Then the iron salt are added, maintaining the agitation and temperature. After the 10 minutes of stirring another 25 millimeters of ammonia hydroxide, concentrate at 33% by volume. It is here that the first evidence of the magnetization of the sample is observed when approaching neodymium magnet. It is left to rest for 30 minutes and washed many times with distilled water until a neutral pH is achieved. Finally, it's taken to heating oven. The magnetic dispersion was stirred for the 1.05 for the second sample with functionalized with silica and polyaniline. With N2 flux bubbling through the reaction sequentially, the resultant ultrafine magnetic particles were treated by magnetic separation and washed several times by ultrapure water and then redisperse into a Q suspension with 50 millimeters and pH 7. The oxidation of the magnetite into maghemite was achieved by raising the pH value to 3 by adding hydrochloric acid, 37% purity, and at about 80 centigrades for 30 minutes. The stirring rate was kept constant during the whole oxidation process. The sample was dried at 60 centigrades, resulting in the reddish brown powder. Then we ready suspense in 48 millimeters of ethanol and 12 millimeters of ultra-pure water. The resultant solution was sonicated for 30 minutes, and the pH value of the solution was adjusted to 11 with the helva ammonium hydroxide. So, as we have the samples, no? For the X-ray diffraction. In the diffraction of the end results, we have in the figure the key here the diffraction profile of the maghemite with polyacrylonitrile sample only displays black peaks of the maghemite phase, and here one must mention that the polyacrylonitrile polymer has no longer range crystalline order with because it's semi-crystalline, and it's overlapped for the maghemite. Consequently, an X-ray amorphous feature in the spec making in the study but X-ray diffraction against the crystalline contribution of the maghemite phase. And this is the Rydberg refinement for we use. The refine the parameters look here and with a chi square 1.13 with the estimated main grain size of the maghemite phase was at 12.5 nanometers. This show in the TEM approximately in 9.5. So, and here the X-ray diffraction only for the polymer polyaniline. This is the second sample, functionalized with maghemite with oxide silica constituting the core, the first core, and the second core is the first shell. In the second shell, is the pani. Well, we the phase the size, the ground size for this sample functionalized the two phase of the maghemite with pani, so oxide silica now not expressed in the profile diffraction with because it's a amorphous phase. So we show the Miller index only for the maghemite and pani. So The imaging microscopy revealed the real nanoscope size of the both magnetic polymer samples, as it can be noticed in here. Core single shell nanoparticles exceed mean particle size of 11.6 nanometers, confirming that the co-precipitation method allows the formation of the nanoparticles with small grain size. On the other hand, the core double shell sample in this figure Revela improves the nanoparticle dispersion by increasing their colloidal stability and avoiding foreign agglomeration. From this, one can expect that also interparticle magnetic interaction become reduced. Well, now the Raman spectroscopy. We show here the Raman spectrum of the here the magamite functionalized with polymer PAN PAN sample was studied with different laser powders, as it can be seen from this figure and here. The corresponding Raman modes are not visible in the spectra with low laser powers. So due to low signal to noise ratio, the broad signal screen the optical Raman modes which is characteristic fluorescence interference due to the organic polymer on here. See, the Raman modes improves their signal at the 0.004. See, and around the 30 70 to 30 90 centimeters on here, here, yes, on here. So additionally to Raman's modes, the 496 here, and 690 centimeters also correspond to the magamite phase according to the literature. The presence of the magamite phase to the Raman modes located at 100 160 and here 100 160 here 100 160 and 100 103.78. But these weak Raman modes were not observed here due to the dominant broad signal. The Raman spectra taken at 0 point and 0.7 also indicate an optical mode of the low frequency region due to the nitrilo group. See here, and evidence confirmed the presence of the polyacrylonitrile and double bonds of the carbon and nitrogen. So the FTR spectroscopy for the second phase with a magamite with oxide silic with PANI, the structure double core double shell. We'll see here mentioned measurements were carried out the transmission mode for both sample with resolution 4 centimeters in the range for the 4000 and 400 of each solution contained the nanoparticle was deposited onto the silicon wafer and dried in an oven at 40 centigrades for 30 minutes. We confirm the presence of the bond of the other polyaniline, polyacrylonitide, the natural group, and well, now vibrating sample magnetometry. Yeah, okay. Excuse me in a moment, please. And the 300K and 5K MH curve for the magamite with polyacrylonitide sample are shown this figure, and this corresponding to the values of the virility to the effective magnetocrystalline anisotropic constant key effect and MS by the equation of the low approximation of saturation. A value of magnetization of the to the 60.3 mg and 68 are obtained for the 3K and 5K respectively. By summing the fixed to the interval plus minus 0.4 kiloesters, some features and magnetic behavior of the simple can observe better we see. And the zero field cooling and field cooling curve measured under DC applied field with 67 Oersted, as can be as the figure and here exhibit broad maxima extending about RT room temperature for the single core shell around the 110 core double shell sample 110. This maximum suggests that the particle size distribution are different in both sample, and some local method could bring some additional information. And finally, the Mossbauer spectrometry, the pro-local information of the iron ions of the cubic spinel structure of the magamite phase. We perform low and high temperature iron 57 Mossbauer measurement, selected Mossbauer of the magamite with PAM, and the other sample with a panning with okay here and for this analysis, we therefore use the well-known sextant patterns for A and B sides of the iron iron oxide for the structure spinel inverse. Additionally, contribution level C of the Maillon temperatures, we added a relation pattern real for both samples on here. So only for the room temperature spectrum on here and on here. For the first sample, the 300 spectrum is broadened and expect for the increasing fluctuation dynamic of the magnetic nanoparticles. Yet the still results sextant patterns clearly prove the magnetic block state, and expect for particles bigger than 10 nanometers. And comparison the spectra to the double coherent, the second, are different with an onset on magnetic fluctuation that become visible already around 100 K. The broader C magnetic pattern increases its weight from the 20% and 20K to about 40% at 100K. Well, so the conclusion, final the functionalization of polymers of the surface nanoparticles of the magamite is verified to the prevalence of functional group present in the spectra of vibration techniques. The first technique, the route of coprecipitation, has lowered to the synthesized nanoparticles, and ferromagnetic behavior is demonstrated for low temperatures as seen in the graph H and MT. However, at room temperature, the different because the size distribution is different, how we see in the TEM. The core single shell samples show the magnetic locate behavior of the 30K the room temperature, which contrasts with a functionalist sample with PANI where interparticle interaction reduce. Well, is all for now. Acknowledge the respective grateful with Peru Minister of the Education, UFES, San Mark University, and CBPF University too. Thank you.
Okay. Time for one question. So if someone wants to make a question in Spanish probably. Okay, or even in English, we can translate to him.
Okay, can be in English. So you produced magnetite from hematite using an acid detect.
Magamite.
Yeah, produced magnetite using an attack on hematite. Using an acid on hematite, was it? Or didn't?
The acid environment. Ya.
Atacou com ácido a hematita para produzir magnetita.
Ya. O sea, la pregunta es si es que la de hematita puede pasar a magemita.
Sí, o ataque ácido.
Bueno, con ácido de esa forma no. Para este trabajo lo que hemos hecho es utilizar el entorno ácido para demostrar que la cobertura de óxido de silicio puede proteger al núcleo magnético. Entonces, cuando se funcionaliza, cuando se agrega, cuando se añade la polianilina, entonces se observa una reducción en el tamaño de las nanopartículas. Entonces, la cobertura del óxido de silicio queda demostrada pues que ha protegido al núcleo magnético. Es así como funciona en este trabajo.
Okay, thank you very much. Thank you to be here, to speak for us, try to speak in English. So just to tell you that Renzo has just finished his undergraduation, so 1 month ago, and he has done this work in Peru as, I don't know how to say this in English, the final course product. So, and then he's explained us what he did, so very good, and thank you very much for that.
Thank you for.
So the next talk will be Professor Eduardo Perini from UFIS.
I'm so used to giving classes that I think that I would not have much of a problem. But anyway, optimizing magnesium and ferrite based composites synthesis by sol gel method for phosphorus removal. The group is quite big, and from a lot of places. Adriano is from Santa Catarina, from the Federal University of Santa Catarina. Will Breiner was working in SAI, and a water treatment company from Linhares, when he did this work. He did the work actually in the lab in Pythagoras faculty, I think. It's not an university, in Linhares. And of course, José Rafael here from campus of Goiabeiras. I am from San Mateus. And Edson Passamani, perhaps you know him somehow. And anyway, the problem that we had to solve, that we're trying to solve, it's a problem that they found a lot in Linhares, is because, well, sewers have a lot of phosphorus. Not only sewers, any place that you have to, in agriculture, you deal with a lot of phosphorus. Because phosphorus is good for the growth of plants. The problem is that phosphorus is good for the growth of plants, including algae. So you have this problem when you put too much phosphorus in water. Everything grows, including what you don't want to grow. So you have this algae, some of them are toxic, and this is, well, not a good idea. And we have a large agriculture here in Brazil, and people use phosphorus compounds in the agriculture, and this goes to the rivers. So we need solutions. Well, we know that magnesium compounds are good adsorbents of phosphorus in water, but there is that old problem of putting an adsorbent that you have to take out later, because it goes down the river. So instead of algae, now you have magnesium. Okay? And then magnetic materials, you can take them out by a magnet. It's natural. So we decided to produce, it was an idea of our student, magnesium-rich magnetic material that might be a good adsorber. We were trying, we were testing, and easy to remove by a magnet. Simple solution. Many procedures shown in the literature are quite complex. They functionalize, they do a lot of complex things to put magnesium in iron. We did something quite simple. We used a method that we've been working with it for the past 10 years. Oh God, I am getting old. Okay, for the past years at least. And only this time we used the lemon peel instead of orange, or coconut water like we did in the past, or even passion fruit we used it in the past. Any big organic molecule here. We mill. Interesting is that this 24 hours is not an accident. This was optimized in the past. Okay? This is optimized to give some properties to the organic. And then we take the right residue, we mill, We are considering if the sieving process is really necessary, because later this guy gets in the water and dissolves. So this control of particle size may be a bit excessive, but for now we're keeping it. And then we did the simple process. We mix it in stoichiometric proportions, that is 2 moles of iron for 1 mole of magnesium, and we mix it with excess magnesium. Just this, we put excess magnesium. Basically anything could happen, but we tried, why not? So we put excessive magnesium here, dry it again to eliminate the water, and then the ferrites produced in the last step. Okay, then we produced 2 compounds. One stoichiometric, it's natural, it's 0, and one non-stoichiometric with excess magnesium. Well, the excess magnesium solved the problem that we've been facing for the past decades, the past at least 5 years. That's when you do by sol gel, you produce ferrite by sol gel, you have hematite. You always have a proportion of hematite. Around 11% is the usual. So although you are mixed in stoichiometric proportions, some of the iron simply do not mix with the magnesium or whatever else you are polluting. So some of the iron always form hematite. It's actually quite troublesome. And when you put an excess of magnesium, you see that you produce the ferrite, 35%. This was expected by the proportion of magnesium to iron, and 66% of MgO. Oh, okay. And we are not showing it here because we sent for publication, but the MgO is, a lot of the MgO is at the surface. So we produced magnesium at the surface of magnetic material just by putting excess magnesium in the mix. This is the most power of the sample, stoichiometric sample. And we see where some of that magnesium went. There is the sextet here associated with Amici-rich disordered phase. So we have hematite, as was shown by the X-ray. And now you see that some iron just really did not bind with magnesium. Okay? The lost material, well, there is, of course, some iron bound with this magnesium, but it's still a magnesium-rich phase. So you have the point is that we have the hematite, you have a magnesium-rich phase, disordered phase here. Basic is this. And when you do it with an excess of magnesium, you have the ferrite, the 2 sextets for the ferrite, normal. You have the hematite, a little bit of hematite still, that X-ray could not find, I think, no? Let's see, I think that no, there is no hematite here, or basically no hematite here. No hematite. No orange here. Sorry, I put this one here, but it's not here. It's not in the spectrum. There is no hematite. A disordered phase. This magenta, disordered phase. And this broad paramagnet component, that's small grains, ferrite. So okay, you put an excess of magnesium, do not have hematite, you have small grains ferrite. It's quite interesting material. It's interesting to see that you have to put an excess of magnesium to get rid of the hematite. After how these years? Anyway, We put this to absorb phosphorus. And the better kinetic model is the first order, the pseudo first order. The pseudo first order model is quite usual. We normally find it in our works. And it basically means that the amount of samples adsorbed does not depend on the number of adsorption sites. When this model works, it works because in one point of the equation, you put infinite absorption sites. The number of absorption sites is so big that their derivative, the reduction in the number of the absorption sites does not count. Okay? The number of phosphorus, the phosphorus atoms that are bound, depend only on the number of phosphorus atoms that are in the liquid. So it's curious that you have a difference. The material with more magnesium adsorbs more, as expected. Okay? And the time dependence is practically the same. You can see here. It's curious because you have two infinites here. You have infinite sites, you have infinite sites. And one adsorbs more than the other. So from a theoretical point of view, perhaps energy, probably energy. Anyway, that's it. Someone told me to go fast, so I went. And that's basically this. The higher adsorption is not due to any change in the structure or composition of the ferrite phase. Oh, that's it. The Mossbauer did not show any difference in ferrite before and after adsorption. So Mossbauer gave, let's say, a 0. There is no interference due to phosphorus. This sometimes is important to get a 0. It's important. People say that the 0 is not good. It's good in science sometimes. To say, no, okay? The ferrite is not interfering in the adsorption. The adsorption is due to the magnesium, probably at the surface. This is an important result from Mossbauer spectroscopy. And magnesium inhibits the formation of hematite and an amorphous phase in the ferrite structure, that small phase. And the adsorption kinetics obeys a pseudo first order model, showing that the number of adsorption sites is higher, quite higher, to the point to be considered infinite compared to the amount of phosphorus dissolved. And these factors combine, and with other things that we cannot show, we sent this to publication, indicate that the samples are uniform adsorbers with a large number of adsorption sites at the surface. And of course, Mossbauer shows that there is no diffusion. Okay, thank you.
Okay. Thank you, Eduardo. Time for question. Juan, please.
Hi, can you hear me? I have one question. Why have you don't write the other kinetics models to try to explain the absorption of phosphorus?
Sorry?
Why you don't have to try to use another kinetic models and correlate them and just use only the pseudo first order model?
Oh, we tried.
That is
Second order, we tried a lot of models. The first order is simply the one that better fits. We tried, actually, we tried everything. And then it's showing only the kinetics. We have also the isotherms. Like I said, we sent this to publication 1-2 weeks from ago. So we are not showing everything here. But anyway, we tried everything. We always try everything. It's simple.
But
we simply try all models.
Is the best that fits that absorption trend data, or is the best that describes the model of absorption on the surface? My order is
No, the benefit to experimental data, including not only R, we include we use all the statistics that we have available, okay? So we analyze everything that we have, and we simply take the benefit. Then we try to understand why it's the benefit.
My final question would be, what would be other competitive absorbents that can interfere in the absorption for phosphorus? Can you mention some of them? Thank you.
We use just a synthetic solution with only phosphorus, okay?
Yeah.
The people from Will Briner, he works at the water company, and the next step is to take a real sample from sludge for sewers and try. But for now, the idea was just to see if we would produce a material just by adding but magnesium is considered a good absorber.
Because if you have arsenic also in the solution, arsenic will compete with phosphorus.
Yeah, it may. It may, because magnesium is not specific for phosphorus.
Okay. Now we are going to hear or to listen Professor César Meneses.
Good morning, everyone. First, I want to thank to Edson, and he's leaving now, and the organizing committee for this opportunity to share with you this the results of this study that we have been done for a long time, and I want to point out here that the name reason is reason for us, but not for the community, because this is an old subject. We know this, and I noticed that in this conference there are several works related with the spinel ferrite. So I want to share with you the most of our studies performed in our lab on ternary and quaternary ferrites. Here M and N means nickel, zinc, and manganese, but there are this family is very, very large. This work has been done with doctoral student Harrison Salazar, and this is a master degree student, Luisa Vargas, Karen Garcia, that is here, from Universidad de Antioquia. This work also, in this work also we collaborate with Carlos Palacio from Universidad Antonio Nariño, and Juan Jaén is here. This is the outline of presentation. Briefly, I will just for the newers, but I noticed that perhaps nobody here is so new in these ferrites. I want to point out that this is with the spinel structure, because yesterday we saw a presentation of ferrites with hexagonal structures, and there are also ferrites with garnet structure. So I want to stress here that the ferrites here is with the spinel structure. This is briefly characteristics that are important for this work. Then the second part of my talk is related with a proposal given by us, in which we can easily and rapidly and directly determine the recoilless factor for samples which has two crystallographic sites. Yeah, and that is the case of the ferrites, which shows iron in octahedral and tetrahedral sites. So this is a proposal of us of how we can calculate in an easy way the recoilless factor, and we apply this for 3 ternary ferrites of this composition. Then finally I show you some results, particularly on this nickel zinc quaternary ferrites, in which here I want to point out the different, let's say, methods to determine the cation distribution that I have noticed that several works are presented here too. So just I want to point out that these are the ferrites that we studied here. This is with the spinel structure, is a cubic system with this space group, and This is the chemical formula. Here M are chemical elements with oxidation state 2+, and we have iron and oxygen. And then we can also write down the chemical formula in this way, in which we explicitly write down the cationic distribution in the tetrahedral and octahedral sites, and this is very important. And we have here lambda is the inversion degree with range between 0 and 1. You notice here that lambda is related with the amount of iron, the concentration of iron in the tetrahedral site. So this is known, so I'm going to say it very quickly. When lambda is equal 0, we have normal spinel in which the divalent cations occupy the tetrahedral sites, and the iron trivalent cations are occupy the octahedral sites. We have the inverse spinels where lambda is equal to 1, we know that. And here, you know, the iron occupies both tetrahedral and octahedral, and the divalent cations occupied only the octahedral sites. And we have the mixed spinels with lambda range between 0 and 1, and this can be the cationic distribution in the tetrahedral and octahedral. This is for ternary ferrites, but what is the case of the quaternary ferrites? We can, this is the simple chemical formula for quaternary ferrites. M and N here means, in the case of our work, iron, nickel, zinc, manganese. You notice here, this is a very common formula used in most studies where M ions are assumed to occupy tetrahedral and N cations are assumed to occupy the octahedral. But when these two cations are distributed between tetrahedral and octahedral, we have found these three formulas, these three proposed formula. We propose this one here, but we have found in the literature other formulas or are equivalent. We can demonstrate that all formulas. But you can notice that M and N cations are distributed in the both sides, and tetrahedral and octahedral. So the question here is how can we determine the distribution of the cations in these two sites, because this is important for the properties. We are preparing these samples because we are making some experiments related with the absorption of water contaminants, and we are we are using these materials, but I'm not going to show the results here in this presentation. So let's start first with the one of the proposals that we have to determine the recoilless F factor, the relative recoilless F factor. But remember that this F factor is, this is the general expression, but if we use the Debye model for lattice vibration, this is the expression here. But I want just to point out that the recoilless F factor is important to us because we can determine the relative atomic molecular weight fractions of iron compounds in the absorbent. That is the reason we want to determine the F factor. This is a well-known formula for the transmission integral, which describes the Moss-Bauer spectra. But in the thin absorber approximation, this formula can be simplified into this one. And we are interested here in the total area. But at the end, the total area is given by this expression here. And I'm going to start with this expression. We start with this expression here. This is the total area. It is assumed of the area components. Here, I is the iron sites of the compound, or if we have a mixture of two iron compounds, then it is assumed of the phases that are here. This formula is already known from the literature, so it's not new. It had been used a long time ago, but I want to point out here that in this formula that is known in the literature, it is useful to determine the recoilless F factor relative to the recoilless F factor of a reference compound. The reference compound here can be iron, metallic iron powder, or hematite, well crystallized hematite. We use as a reference material, we use metallic iron powder that has been well characterized and whose F factor at different temperature has been reported. For example, at room temperature is 0.7, so we use this value. We use this as a reference, and this formula is very simple. You see that here we have the mass of the sample, of the reference material, the mass of the sample, the molecular weight of the sample, the reference materials, and the areas, the most Bauer spectral area. So by using this simple formula and determining the area, the relative areas, we can just determine the relative F factor. This is the thing. This experiment is very simple. It can be done at any temperature, but we are going to show the results for the room temperature that it is usually used in many laboratories. But this is known. What we have proposed, we have extended this formula to compounds that exhibit at least two different iron sites. And this is the case of the ferrites, because iron is located in two different sites, the octahedral and the tetrahedral. So the previous formula is applied only for samples that shows one specific iron site. It's an extension. So how we started? We started with the spectral area. Here with the total spectral area is the sum of the area of the first site, the second site, and the reference materials. Then we divide both sides of the equation by the total area, gives this. And using the expression for the thin absorber approximation, simple, we just use this formula, and we replace in the previous equation, we get this. It's very simple. Then these are the things that change from sample to sample, from ferrite to ferrite. This is very important. We have to take into consideration what we think is the formula that we have for the specific ferrite. This, because we have to know the fraction of the iron ions located in each site. So this is a general, but it depends on the sample. You will notice later when I show the formulas for different ferrite, how it varies from ferrite to ferrite, because this is the starting point here. Then, if we know or we guess the number of cations distributed in both sides, then we can use this simple formula. We replace here. Another thing that we assume is that all available crystallographic iron sites are occupied, so we assume here that O is equal to 1. Here we have the Avogadro number, the mass of the compound, the abundance of the iron, this is the number of iron ions in the compound, and this is the molecular weight of the compound, and this is the area of the absorber. Okay, so look, this is, I'm going to show 3 examples of this method that we propose, the extension of the area. We are going to start first with the case of magnetite. This is a non-stoichiometric magnetite, here X equal node 0. So look, we are using this formula. We have to start with a guess of where are located the iron in the tetrahedral and the octahedral. So we propose this, but of course there is a controversy. We can say, no, there are vacancies in the tetrahedral. No, this is not correct. So this is just to show how it works if we propose this formula here. So the X value has to be determined independently with another method. There are many methods to determine X. So after using the previous equation, taking into consideration the distribution of the irons in both sides, tetrahedral and octahedral, then we get these 2 equations. And we can find here the relative recoilless F fractions of the iron located on the tetrahedral site divided by the F factor of the reference material that, as I mentioned, is iron powder. So this is the formula. You see here that depends on X, the molecular weights of the magnetite and the iron powder, the mass that we use it to prepare the absorbers, and the areas that are determined from the fitting of the Mossbauer spectra. And this is the formula for the other side. You see? This formula depends on what you guess on the distribution of the iron. Please, this has to be taken into account. If we change this formula, then this formula changes too. And this is an example of a Mossbauer spectra of magnetite. We use 10.6 milligrams of magnetite, and it is mixed with 7.7 milligrams of iron. I have to mention that these two masses are not any mass. These masses are in the range between the ideal thickness and the thin absorber thickness. We have to work in this range. Besides, we are also correcting the spectra mathematically from the thickness effects by using software. In the case we use recoil. So we correct from thickness effects this spectra. And then we fit, and this we show here some results here. By using our method, we found that this recoilless factor relative is 0.97 for tetrahedral and 0.92 for octahedral, and the ratio between the two iron between the two gives 0.95. This is very, very, very similar to a value reported earlier of 0.94 by using a very complex method. So we are proposing a direct and simple method to determine relative factor for samples that exhibit two sites. Now let's show you here an example for another ferrite, that is nickel ferrite. Look, we have to start with what we assume what is the formula for the distribution of the iron. This is important. This is the starting point. This is what we think is happening with the sample. And then we use the previous equation, and we derive these two equations to determine the recoilless factor for the irons in the two sides for this ferrite. You notice that this formula is different from that of magnetite. I hope you notice, especially in this factor here. So lambda has to be determined also independently. So how we determine this? We use, we simply take the X-ray diffraction, and we determine the lattice parameter, and then we use this formula that this is already known in the literature, and we assume explicitly here that nickel can be at both sides, and tetrahedral and octahedral, and we just simply compare. This is the theoretical line, and we just see where cut here, where is the crossing. This is the experimental getting by using Rydberg refinement of the X-ray diffraction, and we just get the value of lambda. We need the value of lambda, and then with this lambda we can go to the previous formula and just replace, and we can get the recoilless. Here we show some examples for this as a 300 Kelvin. For different mixture of max mixtures for metallic powders and the ferrite, and we get this value. I want to say that this value is different from the value of that we found for magnetite. So I want to say that please be careful when you use, because we normally do the following when we want to quantify the iron in a sample. We always assume F equal 1 if we do the experiments at room temperature. This assumption that F equal 1 is valid only at very low temperatures, where F is almost equal 1. But if we do the experiments at room temperature, F is not equal to 1. And moreover, the relative F factors for the B to the A sites are not equal to that of magnetite. That I have found that this also another common, I think, error in the literature. That most papers use for every ferrite, doesn't matter which ferrite is, they always assume that this coefficient is equal to that of magnetite. It's not equal to that of magnetite. This, at least this is what we found for the samples. Of course, this range from sample to sample. And finally, we did that in the third ferrite. This is again the same. We have to start with what we guess about the distribution of iron in the two sides, and then we derive these two, and then we again do all experiments as before, and then we get this value is not equal neither to nickel ferrite, neither to magnetite. It is different. So I think that what we have found is that be careful, we cannot use the same F factors for all ferrites. Don't use that on magnetite because it can be different. Okay, now I'm going to show now, was our first work. It's a very simple one, but it is just to share that I want to tell. And this is another work. This is related with it's another different work. This is related with quaternary ferrites, but I'm going to start with ternary ferrites. Here I'm going to assume x equals 0, so we have the nickel ferrite. And we want to show that with using 3 or 4 techniques, we propose that perhaps there are thermal treatments at let's say low, this is not low, but comparing with the other, at these low temperatures, cation vacancies at the octahedral sites can be formed, and these are gradually filled with iron as the temperature increases. That's what we want to show experimentally that is happening in our samples. So what we did, we mixture nickel oxide and hematite by using ball milling at very low energy, just to mix the powders, and then we submit it to 3 different temperatures. Here, the first X-ray diffraction is for the mixture, the simple mixture. The X-ray diffraction for B, C, and D are the patterns for different temperatures. This is Rydberg refinement. From there, we have we determine the lattice parameter, and we can notice here that as the temperature increases, the lattice parameter increases. So we try to explain why this increasing or what this variation is a parameter with increasing temperature. What is how it happens? We try to explain using this well-known formula that is only based in cation reordering phenomena. Yes, it's just by checking the ordering, that there is a redistribution of the cations in the 2 sites, in the tetrahedral and octahedral sites. But we notice that this theoretical formula cannot explain these results, because with lambda equal 1, we have this lattice parameter that is close to the one at 1200 sample, but the other one is not in this range, is outside. So we need another explanation, and we propose that this is due to cation vacancies on the octahedral sites at low temperatures that are gradually filled up with cations as the temperature is increased. We start with this idea, and then we check Mossbauer spectroscopy again. This is for the starting reactive. This is at different temperatures, and then we determine the area. Look at the area. I want just to point out of the area. Look, the area ratio of the A to B site. Look how it changes. It is high, and then as temperature increases, it goes to 1. How to explain this variation of the relative areas? We notice that it can also be explained, as we explained before, that the samples at low temperature, let me talk about low, 1000 low temperature, it has cation vacancies, but as temperature increases, there is a filling up of these vacancies. And there is no cationic distribution. It's not due to cationic distribution, as is assumed here in this formula. This formula can be obtained from the previous formula and also it is published in the literature. We found that when lambda equals 0, or you can notice here that when lambda equals 0, this ratio is equal to 0. And when lambda equals to 1, this is 0.92 if we use the value that we published in the previous result. So this is reverse, the reverse of the other. That's why that it gives the value 0.92. So because this is outside this range, so we cannot explain this variation in the area ratio as due to reordering phenomena, because this formula is only due to reordering phenomena, cationic distribution of the cations in B. So that we have to find another explanation. And the other explanation is because the area is proportional to the number of iron atoms, then we can just guess that the irons at the B sites becomes populated, and means the vacancies are occupied as temperature increases, and then this is nicely in agreement with the X-ray diffraction. Now we can do that the same with, I'm just going to talk about infrared. Infrared, this is for the mixture, so I'm going just to concentrate on the thermally treated samples. We notice that this first band is due to iron oxygen stretched vibrations on the tetrahedral, and this is on the octahedral. And we notice that the octahedral increases slightly in intensity, Okay, we can do that also by fitting here this Raman spectra, but we did not. Here we showed some SEM micrographs, and we took 3 zones for typical samples, this blue, red, and green, and we, by the EDS spectra, we determine the chemical, qualitatively chemical compositions in the 3 zones, and we notice that as the temperature increases, the zones becomes homogeneous in the distribution of the ions. It is very interesting because it also is in line with the previous interpretation of what can be happening with the temperature. And finally, I want to show this because we can also determine this is my hysteresis loop. Sorry, hysteresis loops of the initial reactants and for the 3 different temperatures. And we just want to concentrate on the saturation magnetization, and you notice that as the temperature increases, the magnetization increases. How to explain this? We can, because I saw earlier work yesterday that perhaps there is a canting, and with this formula we are not assuming canting, we are assuming that there is a this is a collinear antiferromagnet. Yes, please. This I'm going to start, but we want to say that this is what we believe can be happening with the sample, and if we assume just cationic distribution, then this is the formula. We have here the saturation magnetization per formula unit per unit cell, and we have here the magnetization at the B site minus the magnetization at the A site. The magnetization at H side is due to the magnetic moments of the nickel plus that of the iron at the concentration, and this is for the B side. These formula are known. Then using the electronic configuration, we know that the nickel has 2 iron at the D level, and iron 5 at the D level. So we replace here by multiplied by Bohr magnetons, and then we find this formula here, but we notice the following. When lambda is equal to 0, then we have a value of the M theoretical, but when lambda is equal to 1, it means that if we change from 0 to 1, then this M should decrease. But this is not observed, it's increasing. So again, cationic distribution cannot explain the behavior of this. Then we propose that this is perhaps there are vacancies, we put here like B, vacancies that are gradually filled as the temperature is increased. Okay, now I'm going to show the final work because I don't know how much time I have, but this is due to this is a quaternary ferrite, Xe difference to 0, and we replace nickel by zinc. Nickel is magnetic, and this is a diamagnetic zinc. And we here show the typical solid state reaction method to prepare the samples. I want to tell you something and before continue. There are many methods to determine the distribution of the cations. I have shown formulas before for ternary ferrites. One that comes from Mossbauer, the other that comes from X-ray diffraction by using the unit cell parameter, and in the last result I showed also from the saturation magnetization. But I want, perhaps you know, from X-ray diffraction we have two different ways to determine the cationic distribution. One is from the unit cell, the lattice parameter as shown here. You see, this is the theoretical parameter where we can have here the radius of the tetrahedral and the radius of the octahedral, and here we can put whatever we want, but with physical meaning. You notice here that we are not saying that nickel is only for the tetrahedral, but we assume that we can have nickel at both sides. This is important how you start assuming this. We have here the concentration of nickel in the tetrahedral, and this is the radius of the nickel at the tetrahedral side, assuming high spin and also the 2+ oxidation state. The same for zinc and for iron at the tetrahedral and also for the octahedral. So if we know this, of course we can determine this by using just, but we have here 3 variables as just one equation. Yes, 3 unknowns and just one equation. So it is difficult. We have to combine with different methods. But this is a method that can confirm that our guess about this cationic distribution is determined. So we did this. We compare this using Rietveld. We compare with the theoretical here, and we compare also determined by the Nelson-Riley method. Is also another method. Did not give exactly the same as with the Rietveld. It's not the same. And then we compare with references of nanoparticle and also with another people that prepare with bulk, and this we compare. Look, this is another way with X-ray diffraction. There are 2 ways for the cationic distribution. This is using the intensities of the lines, but not all the lines, specific with the some Miller indices that are very sensitive to the cationic distribution in tetrahedral and octahedral, and we can use this formula. Again, here is very important that because we use this formula based on this cationic distribution, but if we assume another cationic distribution, then this formula change. This has to be, you have to take care on that, and then we compare the theoretical and calculated for some lines that are reported that are sensitive to the cationic. Some lines are good, some are not good. Other method, you see, there are 2 methods now that I have told that. 2 with X-ray and now with Raman. With Raman is also possible to do that when we concentrate here on this band here. And here we show a fitting showing the 3 components fitted with Lorentzians. And from this formula here, and determining the intensities or the area, we can determine the zinc content at the tetrahedral. So we determine that way. From Mossbauer, we can do that. This is at room temperature. This is at low temperature. We use again. We have to know. We have to propose formulas for the distribution of the cations. I want to say also another thing about Mossbauer. We can also determine the superexchange interaction on the octahedral side by using this proposal of equation by assuming some interactions, but we determined in our samples, we determined 0.9 Tesla, and this is very close to value reported by Lung and Evans in 1973. that it was about 1.2 Tesla per exchange interaction. It is good, let's say, is between the range of values. Okay, this we compare the three techniques to determine the cationic distribution. There is possibility to use also magnetization measure, but is not shown here. Just want to say that we can do the same as we did with the zinc ferrites. We can do the same with magnesium zinc ferrites, these quaternary ferrites, and we can do again the same analysis, and we can compare. But just to tell you that this is a work that is going on with these samples. So let me summarize because it's time. I just presented in summary three things. First, we propose a simple formula to directly determine. We did it at 300, but this can be done at any temperature, at single temperature. There is no necessity to do temperature dependence of isomer of absolute area. Just one single temperature, and we derive some formulas to determine the relative recoil F factor for two sites, not only one, as assumed in this when we use this method. And we use it on ferrites. We apply this methodology to 3 ferrites. The method can be applied to all ferrites, to any ferrite at any temperature. The second work that we show here, we think that we prepare nickel ferrite is formed at at this temperature at 1000 Celsius degrees, but as the temperature increases, the defects gradually disappears. Neither cation reordering phenomena nor possible evaporation of chemical elements were the dominant effects to account for the results. I hope this is right, the analysis. The results can be explained if we assume that the cation vacancies on the B sites are gradually filled with cations as temperature increases, and this is the third result. We can determine the stoichiometry of ferrites by at least we show here 4 methods: magnetization, X-ray diffraction by the lattice parameter, and also for the intensity of some X-ray line, not all the lines, but some specific lines, and also Moss-Bauer spectroscopy, magnetization, and Raman. But there are more methods, not only that, SABS, neutron diffraction. There are many methods that, and we need to compare because we have noticed that not all the results are sometimes comparable. So we need to take care on that. But it's good to have a comparison of the different methods and to see how the stoichiometry or the cation distribution in the 2 sites can be determined. Oh yes, that's all. Thank you. Thank you very much.
Okay, thank you, César, for this very nice talk and to show us how important it is to use Moss-Bauer sometimes, and then you can get, for example, information about this very old system, but is still very, very recent in the scientific point of view. Some questions? Please.
Could you please show the last infrared? Yeah, it can be this one. You see this last, this higher frequency vibration here? The higher frequency, yeah, no, the higher frequency, the one that you didn't identify. It was identified by the group of, I think that was by Czechvelak, I'm not sure. This is usually associated with vacancies, this last one. Yeah, because when you do not have an oxygen linked, actually it's the oxygen that's vibrating. If you do not have an iron, the oxygen is vibrating free, so the frequency increases. the stretching frequencies increases. I have a set of articles stating that this last one is due to vacancies. Okay, not published by me. I think that's the group of Shaplek. Sorry, but because my memory is not so good. And there is also a theoretical one about where the vacancies are more likely to happen. Again, I do not remember. Okay, but if you ask me later, perhaps I just wanted to show that you see this last one here, this the high frequency. It seems to be disappearing. Yeah, I'm not sure, but it seems to be disappearing. No, broadening at least. No. And it for sure is because you have oxygen and do not have iron linked to it. And it changes depending on the environment. Because it happens, for instance, in silicon, there is something similar, where when you have vacancies in silicon, you can see the size of the vacancy by the frequency. Because the frequency changes when you have more free space around the, let's say, the harmonic oscillator, okay? Okay.
Ganesh.
Thank you, César. And you are right in giving some information about be careful on the problem of ratio, tetra, octa, and so on. So I have a question. It is related to previous table, I think. No. Yeah, that one, yeah. Because you show finally how to say the difference using 3 different techniques. But according to my view, the values are not so close because you have 0.20, 0.24, 0.46. So, for example, for Raman at the end you have 0.77. So I have the first question is how can you explain this? And the second one also is are you sure about the initial composition? In terms of nickel, zinc, iron content.
You are right. When we started to study this, these are the results that we get, and we found that it's very. We have to be very careful the way we determine it in each method. The way we determine these parameters. There is a large overlapping of the in all techniques. You mentioned that it is better to have separated lines, isolated line, but this is in all these techniques there is a high overlapping of the lines. This is one. The way we start the calculation also is important. We have a lot of assumptions. We have in each one of the techniques we make assumptions, and this every time we make the assumption, we affect the results. Yes, because it is what we guess. I have to say that we made that. In most of the cases, we have only one equation and many variables and many unknowns. How we determine the others unknowns? That's another thing. So there are many things here. And I noticed the following. Not from our work, but from the literature. I noticed that some people start determining by Mossbauer the cation distribution by assuming the wrong F factor, and then we use this X and replace it in the X-ray diffraction to do the analysis. And others do the contrary. Start with the X-ray, and then we get the so there are many ways. I think that we need to work. I think that I noticed that we need a real work that tell us how to proceed under such an amount of variables, which technique is better for that, which technique is better for that, which unknown we determine first. So it depends on all of this, but we determine this separately. That's why I think it is accumulation of assumptions that make this variation. Of course, the sensitivity of technique is different. No, this is X-ray. This for the cloud, the electronic cloud, and they can be overlapping. Our Raman is also start with the laser, red laser with the low power to avoid the change of phase. And so it's light and it's scattering. There is another physics behind, and more power is also. We have to take care of this.
But when with this table, it's difficult to convince people which technique to use.
Yeah. No, I don't want to convince here none of you. I
Okay,
just
great.
want to call you the attention that we need. I think we need a work. I think we need a work to answer that questions. I just want to say there are many methods to determine the cationic distribution. Then there is no one. But which is better and why? This question has not been answered. And I noticed that all the works that have been published, at least the ones that I have read, always assume results from previous technique and then use the results for the other technique and then for the other. But why not to start with the other? Who is right? I didn't. This is work that I didn't do. See.
May I suggest something to put some error bar?
Okay. Yes, that's right. That's true. That's true. Yes. Okay. Thank you. Yes.
Easier to compare.
Okay.
Gustavo?
Okay, thanks, César. Very nice talk. I have two questions, very easy. I was wondering if you have think in some collaboration with some calculations people, researchers about I don't know. And the other one is if it is possible to use, or if you have think to use something different than to alpha iron, some spectra with only one line or two lines, so it is not so invasive over the spectra.
Thank you. Thank you. So yes, of course, I think that the idea of LACAME is that we can. It's very nice to the suggestions you have that to find collaborations, because at the end we need to understand why these things happens, and we have to combine. I think we combine techniques, and if we combine with theoretical work, it works very, very, very good. So we are. Thank you. It's a good. We are open for that kind of collaborations. Yes. Sorry, the second question was for, yes, we can, we use iron, 50 iron, metallic iron powder, because this is a well-studied sample, and we use as a calibration also, but of course the iron foil, the metallic iron foil, but this is a standard. We know that, so we can use any standard, no problem. We use it hematite also, but the problem with hematite sometimes is that there is a superposition of these lines with that of some of ferrite sometimes. So it's not good. Talking about what Jean-Marc presented in the previous. So there is no, let's say, requirement about the reference. The reference is just a sample that we need to know very well. It's very well characterized. We know very well the F factor. It has been determined at different temperatures because we use this as a reference. Yes, that's the requirement. So we can use a single line. It should work. Just we need to know the the value of the factor at any temperature.
Hi, thank you very much, César, for your talk. It was very interesting to see that people actually use the F factor to extract information, because you usually don't care about it. My question is regarding this table that you see here, you show here, and the measurements in general that you showed. And when you use the F factor, you are taking into account also the lattice dynamics, because you showed this formula here there, where it also depends on there is this D by temperature and so on. And I see that table, and I was wondering if the X-ray diffraction and the Raman spectroscopy were measured at the same temperature of the most broad spectrum, because in that case you more or less would be guaranteeing that the lattice dynamics would be at the same conditions for all the characterizations, and then probably you would reduce. I was thinking that probably you would reduce the discrepancy between those values. So I don't know what you can comment about that.
Yes. This method does not depend on the model, lattice dynamic model. It's independent. So doesn't matter if the bi or a more complex lattice dynamic model. This is an independent model. You notice that we just use the formula of the area. I didn't care about the physics behind the dynamics of the lattice. It's not taken into account. Second, yes, all the experiments were performed at room temperature. X-ray, Raman, hoping that the sample is not heated when you impact with the laser, and yes, the Mossbauer and is performed at the same temperature, so we can assume that, yes.
Hello, César. Very nice talk. My question is, maybe you have told us before. If so, I apologize. What is the mass ratio between your sample and the reference that you use normally, and how you decided that criterion? Is that the best one? It will be another one possible?
Thank you. No, there is no rule for the amount. I just want to stress how to point out. That we, for example, the important thing is that this, for example, this. Here we use the iron, and for the ferrite, we use these amounts. It's totally arbitrary. There is no rule for that. It should be independent, because we just use this formula, and this formula doesn't mention what should be the value. But we have to take two important things, I think, into consideration. First, that this mass here is not any mass. This mass is between the range of two masses. That the ideal mass that is derived from the ideal thickness, taking into account the area of the sample holder, because you can change the sample and then you use another different value. But you have to be careful that you are below the ideal thickness, and you are above the thickness of the mass. That this, of course, is zero. The mass that does not produce thickness effects. This is the first thing. So the mass has to be in this range. The mass of the reference materials are from the ferrite. I work within these two. The amount is arbitrary. You can choose any value. What we did, we can also we mix, let's say, for example, 200 milligrams of is 100. I'm going to say something here. 120 milligrams is iron, ferrite, and the rest 80 milligrams is iron. We mix fully, and then we can take from this mixture a small amount in such a way that we are in the range. This is one method, or you can just mix whatever amount. And the second thing is that we perform thickness correction by software.
I know, yes.
And then and then we use, of course, this is also it has a lot of assumptions. It has assumptions. You use the recoil program to do the thickness correction, and then we fit it. And
No,
these values are
the
after
sense of
testing.
the question is that maybe if you do error propagation of that expression, it may appear that some the relative error of the determination of the relative factors is larger for some mass ratios than for other mass ratios. That
yes.
it would be possible. Have you done that analysis?
No.
Okay.
No.
No, it's okay.
Okay, no,
Just a
thank you.
suggestion.
Thank you.
Thank you.
This is the 11.21 milligrams of the mass of the iron in 1.26 circular diameter of 1.26 centimeter in diameter sample holder, and this MTSD for the
total.
ferrite total for
Total.
ferrite is 14.39. Yes.
That's the total. So let's thank the speaker again because it's already almost. Thank you, César, so much. Gustavo. So the next talk will be Professor Gustavo Pasquevich from Universidade Nacional de La Plata. He's going to talk about characterization of magnetic nanoparticles and ferrofluid by Mossbauer spectroscopy.
Okay, thank you to the organizers, Edson, Rafael, and all the committee. Also to the people of Vitoria, of Brazil, that are here, and why not to all the community. Okay, I will talk about characterization of magnetic nanoparticles and ferrofluids by Mossbauer spectroscopy. In fact, I will talk about magnetic nanoparticles in powder that became from a ferrofluid. I was with the intention to take here some frozen samples, but it was not possible, so I will remain only in the powder samples. Okay. Okay. Francisco Sanchez say something about where we come, but I will say that to those that have been in La Plata, in last old LACAME', when we were at that time, it was in 2008, we were in this building, the institute was in this building, and it's moved, has been moved to this new building in 2018. When it moves from this building to this new building, I was designed to, I don't know why, but to move all the Mossbauer laboratory from this to this institute. So it was a hard work, and when it ended, I was put as the responsible of the laboratory of Mossbauer. So, oh, it's fast. Well, some of the difficulties I want to point that we have the most difficult that we have. It has to do with, at the moment, with how to take the Mossbauer source from Russia to South America or to Argentine here at the bottom. So yesterday we were talking about some solutions, but I wanted the slide here because it's something okay. Okay. The laboratory where I work, it has 5 spectrometers. At the moment, only one, and the second one with a cryostat of closed cycle or Chinese. We expect in the next month to start to work with this the spectrometer. The idea of the laboratory when it was founded, when we moved, is that I'm speaking fine. You listen me because I see
The idea of the laboratory is to be a laboratory to all the institute to help the different lines. We have the lot of lines and people that has been formed in mobile spectroscopy. So in a shared way of think, we are open to anyone that needs some characterization, internal surveys. Also, we make basic research investigation in all from the different lines in the laboratory and also of mine online, applied research, and we have external surveys. In fact, what my idea is that it has the source that is both should be working all the time in efficient use. In that sense, in the pandemic, we design a multiple sample holder to be able to manage the position of the sample remotely, while the restriction of movement was not able. And it was a good idea. Today is still working because we have a room temperature spectrometer. When we move the source to this situation, it will be different. But up to the moment, it is very efficiently. You change up to 9 samples in one time, and so you don't irradiate yourself too much, and you can measure, select a measurement, and decide if it move to another sample, study the measure if it is fine or not, and if it needs more statics, you can move again to the same sample and go ahead. Okay. My work is related with magnetic nanoparticles in monodomain state. Generally, we use work in applications in biomedicine, but the application of the characteristic of the nanoparticles can be applied in other situations. It has to do, the properties are mainly related with the relaxation characteristic of the nanoparticle system, of the monodomain systems. This relaxation allows to extract heat when you apply a radio frequency field over the nanoparticles, and also you can operate over the sample, the nanoparticles, translating or rotating them with the not uniform magnetic fields, or if you want to rotate but not move, with uniform magnetic fields. So for the project that I was working at the moment, with the thing that I will show in the next, we use the co-precipitation method to obtain magnetite or magmite, because they're a mixture of nanoparticles. We choose this because we were interested in some biomedical experiments, and we need a lot of samples, also because of the physical characterizations of the experiment that we want to do. So it has this technique give you a lot of samples. In one only synthesis, you have 500 milligrams of magnetite, that in a Falcon you give 10 milligrams per milliliter. Is a lot, is very much. Okay. The idea that is behind what for what was the particles is to put them inside the cells and promote the formation of aggregations inside the cells into endosomes, and with some magnetic field generate chains, and then if you move the chains, you rotate the chains inside the cells, you can maybe promote some broke of the membranes of the cells. Okay, in the first video, Rafael, if you want to put me, thanks. Okay, here only to show you what we have with a lot of hard work advanced in what is the characterization of the movement, not in cells, but that it has a lot of study on how it should be the field, which is the design of the field, and how we can distinguish movements and how we can quantify the movements. And the idea was always try to use a microscope, and as they are low frequencies, and we want to see aggregates, it's possible to use a microscope. So it takes a lot of time, and I want only to show you that the difference that we can find if we think to apply oscillatory an oscillation field. You see some changes, maybe, I don't know. Yes, it can be, but there is some alignment, but the particles change its magnetizations itself and only remains the alignation with the field. You don't see a chain that moves 180 degrees. In the other case, Rafael, if you can't, we have add a DC field, and we have seen changes, important changes in that situation. So there is this is the nanoparticles in a B-layer over, they are in an aqueous system, but are over a chloroform to see them without friction with the bottom of the flask. Okay, we pass. It's only to show you what I'm doing, because what I will do, sorry, I have to move it. Okay, in the what we have done with the nanoparticles in the biological area is only to test that they are not toxicities in the range that we have tested, and that they have go inside the cells. We could see it through BSM and also by TEM. So in fact, what I will talk, it has to do with that and with that, because we arrive at the moment that the 50 milliliters of Falcon start to end it. And we have a lot of experiment just done. So we have to make another synthesis, and we hope to have a good repeatability, because it's necessary to continue with biological experiments and don't lose what you have done, have similar systems. Okay, and the result will be that we have a lot of variations, but I will discuss about what we can learn of this variation from both our spectroscopy. Here we have the first synthesis that was done. It was some problem at the end, and we don't have the nanoparticles to use in the biological, so we make another synthesis, the same synthesis, and we saw that that was a very good coincidence between, we saw by Mossbauer spectroscopy that was a good coincidence with both nanoparticles in particular. So all the biological experiments, the first biological experiments, and the only we have at the moment, were done with this synthesis. But it started to end, and we pass to need another one. And that was what's happened. Okay, we made the synthesis, and when we check with different techniques, in the case of Mossbauer, we see that situation. And it was not so different. They are normalized by area, but there is some difference. This line is narrower than the other one, so it seems that the particles are bigger in the new synthesis related to the first one. So in Argentine is partido, revancha y bueno. So desempate. We make a third synthesis, and the result was not equal to the first and not equal to the second one. Here appeared something different. We have again the same situation, but in the other side, we have the presence of two peaks. Also, it's like we have, it's more like magnetite than magmite that was the first one. Okay, so that I will talk about this kind of this synthesis we perform in this work that it was presented in last LACAME. At the end, we'll put the reference, and in this presentation, I will put some new advances and some collateral tools that have been obtained from this work. Okay. Not all, but almost all were, some of them were characterized by X-ray diffraction, and we don't see any presence, only magnetite and magmite. Okay, we don't have a good access to X-ray diffraction or easy access to X-ray diffraction, but we wanted to know about the diameter because we were discussing about if they were bigger or not. So we concentrate all in the main peak to be able to make sure in the main peak. And we can obtain diameters from this main peak. Here is only consideration about if you choose, you care about experimental broadening or not. It's important, it makes a change. It makes big changes in bigger particles where particles are narrower, and maybe not so important in lower one, but you have to take into account. Okay, we also characterize the samples by magnetic magnetometry at room temperature, powder samples and liquid samples as ferrofluid. Random or powder samples can be analyzed or must be analyzed with a model or random model, magnetic random model, and random distribution of anisotropies, I have said. And in the case of ferrofluid, it can be analyzed with a free to rotate distribution of Langemanns. Sorry, because of the English, yes. For this this study we don't have made at all up to the moment. We can't do it, but we I don't know why we don't have done it. Sorry, but it takes a lot of time. It takes a lot of time. We can analyze. I will discuss in the next slide something about the asymptotic behavior, and related to the Langemann, we have a tool that makes it fast, the analysis very fast, and it's easy to test different initial values and play with the initial parameter to get a good fit. So from powder samples, in fact, we work with the asymptotic behavior, where we have just a few months ago make some study how we can obtain information about the mean magnetic moment and the magnetic saturation. That is very easy because if you know the sample and you measure magnetic saturation, divided the mass give you the magnetic saturation, and the relation between the anisotropy, effective magnetic anisotropy related to saturation magnetization. All this information can be obtained from fitting the asymptotic behavior. So we characterize that. And from ferrofluid, you can you have a good information about the magnetic moment, weight by magnetic moment, or the mean magnetic moment. I like more the information weighted by magnetic moment that is like weighted by volume, volume. Okay. So, and here we have the difference Morpho spectra. You can see that they're almost the same, but with different, very, very different features. So how can we understand this difference? And the first thing that we know that was happening is quality magnetic excitations. That is something that takes or to introduce Murray and Topse in 1966. I was 1 year old at this time, and it has to do with what you have a monodomain particle, and is and it's if it has a very fast relaxation time, it will be like a paramagnetic cycle because it is half and half in both sides. It has a null hyperprime field, but if the time it's shorter, it will be only in one of the two wells. But maybe the thermal energy let the magnetic moment, the superparamagnetic moment, be oscillating inside the hole, so you will have a reduction in the mean magnetic field that is higher, this reduction, as the particle is smaller. A smaller particle, higher the reduction. This is an approximation that gives Morup to valid to high temperature or low or high volume, sorry, and low temperature. So what you will see if you have something that very big, lambda is kV over kVt, so lambda is proportional to volume. I will say lambda a lot of times here. When you have high lambdas, you have the bulk spectra, but if you introduce the volume, you will start have the same spectra, but shifted because of hyperfine field. So in our sample, we have mixture of magmite and magnetite. So we have sites for magmite, for iron in magmite, both sides, and also for magnetite, both two sides. And what else? Well, we should care about. We will deal with the fact that the collective excitation occurs in the different sites. Each site relaxes in a different way because this relation. Because this relation, yes. Also, we can have surface disorder, loss of homogeneity, a lot of other things. But the more what I understand or what I have proposed is that the most important things that occur in our samples are related to this situation. So we will focus in this one at this moment. Okay, here the one of the spectrum that was is fitted considering a distribution of magnetic fields, but taking the isomer shift fix as they only are affected because collective oscillation, collective excitations. Only the magnetic field is affected. And we have a relatively good spectra. We have some difference here, some difference maybe here, but it was well fitted. In fact, the hyperprime field, the isomer shift, I don't have here, but it was not exactly the one of the magmite. What's a little higher. But the fit is good, the fit is good. However, with other samples, we start to see that it's not possible, or we observe that it was not a way. So we try to make a distribution of magnetic-like sites, two sites, one sected for the irons in the tetrahedral and one another sected for the iron in the octahedral sites. And both reduce it because the size of the particle, the volume of the particle is diminishing in the same way, sorry. And the result was different. Here we have a good fit here and not so good here. In this case, we have better here and not good here. So there is a mixture. And to take the mixture, we have to make a fit with the two models. Each one of these models in my laptop that is in some seat in that place takes around 2 hours, each one. And the last one also. The last one also. So it was very difficult to think that it was possible to fit two distribution of two different sites distributed in different ways. So we decided to go to something to assume that the distribution of size is log normal. We have a log normal lambda distribution that is translated to the hyperprime field in some shape. Here we have how we transform a log normal volume in a log normal lambda is the same, but in hyperprime field it takes another expression. This log normal is related with this distribution, and here small particles are related with this. Higher particles are related with these other particles. So in what next, maybe I will. We always assume that the fraction of spectral area is related with fraction of total iron in the contribution, and that is related with fraction of total volume particles related to the contribution. Okay. Then we have in our samples, magnetite and magmite, we have two sites for for magnetite and also for magmite. So we will have different hyperfine fields for each side, but the volume of the sample and the superparamagnetic moment is oscillating in the same way. So the hyperfine field of the irons in tetrahedral or octahedral side reduce in the same way, So we will use that to say that both spectra should reduce in the same ratio. So in that way, we are able to have a distribution. If we have a distribution of sizes, we will have a distribution of hyperfine field, and we can then calculate which will be the nanomagnetite or nanomagmite spectra that are here. This is a proposal of how the bulk spectra is affected because of the size. So for do that, we need a bulk spectra. We are working with. I am working with nano spectra or nanoparticles. So we go to the literature to look for. It's not very clear, right? To look for bulk spectra. And we take the one for magmite. I take the one of Da Costa of 1995 and from Van den Berge of 2000 for magnetite. I only point that at the beginning, I have as a reference paper, I like to very much, a list of a review of McCammon, of Catherine McCammon, that has a lot of data of different systems. And in fact, it has also the hyperfine parameter for magnetite and magmite, but they are not updated. And the first part of the work, I have done it. We have done it with these parameters, with some difference when we move to more updated data. So we have the parameters that are isomer shift, are relative fractions from what the author have measured in bulk samples, and also relative line width, because it's important to have the shape of the spectra. And we only will change the magnitude of the hyperfine field, only that. In that way, we fit all these spectra. In this fit, the parameters are the background, the area of the magma like, gamma of each side the same gamma. Each contribution of each magmite sextet have the same gamma. The lambda 0 and sigma are the parameters of log normal. Log normal used to have two parameters. And from these two parameters, you can calculate the mean lambda, the mean volume, is like the mean volume. So we are able to have mean lambda for magnetite, mean lambda for magmite, and also, because of the areas, mean fractions. So I will tell you a little about the code, only this slide, and the next one with some examples. It is made in Python with all this package. In particular, this one make it interactive, to work interactively through a console. And it uses the package uncertainties that from Python that is very useful. It is package that let you make propagation of errors in very automatic way. And the LM-fit, that is the heart of make it fast. That this go easy to the results, I will say. And I want to say that LM-fit is a code that is it's written, or was initially written by Matthew Newell. That is the same that has made Artemis and Athenas for XAFs and SAS. Okay, and what else? The models, the model for the sextets is not the idea of how to have different sextets, different doublet, different angles, how we correlate and Boytians. All that came from start with some I don't know. I have asked, nobody can tell me, some program in Fortran with cards that were translated Fortran in PC. No, Fortran is translated from TEDPAC for correlate angular perturbation to Mossbauer by Mercader. Then Sanchez also makes some big contributions, and Luis Mendoza Celis introduced using papers from Vandenberge, introduced the Voitians to this software. Here I have the picture of Luis because he has passed away a few months ago. I wanted to say it and to put the picture in the slide. So then, in my first days as student with Kike, we translate OTLA to something more easy to work than Fortran, that is MATLAB, and the laboratory, the people in the laboratory start to use this software, and in particular, Luis Mendoza, when he was working with this kind of code with this name, he gives me a lot of books corrections, and one time he say me, I have some correction from Mala, that is like bad. All we need what is Mala, and he puts the name to these things as Mala. So this code is now called Mala.py because it is in Python. Okay, and it can be used also to fit anything. Here there are nanoparticles made by decomposition, high temperature decomposition, and this one, these are the same. Are from the last work that present Kike on Monday. You can ask to him what this means. Here is the difference between fitting with the Voitian and fitting with the nano magmite contribution. We have this option. Okay. So, but the problem is that we have two mean values for lambda from magnetite and magmite, but that doesn't point that magnetite are higher than magmite, because lambda is the product, I don't have it here, the product of constant of anisotropy per volume. So it's the constant of anisotropy. So we can take or to talk or to discuss about sizes, volume, we can transform the sizes that will have the particle of magnetite if it were magmite. So we divide by the constant of anisotropy of magnetite and multiply by the constant of anisotropy of magmite, and we have the sizes it will have. So we go from this value to this value, smaller but bigger. So in this case, we can see that the particles say that the particles of magnetite are bigger than the magmite. But with this procedure, we can calculate a mean whole volume lambda mean value. That is related with the distribution of the size of distribution of particles. Here we have the final table with the sizes of the nanoparticles and the fraction of magnetite. Okay, and I'm ending. I don't see it's on here. No. Okay. Okay, but I will end anyway. Okay, and here we have the correlation between within the results that we obtain with the other techniques. In fact, here I have the correlation of the lambda with X-ray diffractions. Here it is the 1/3 root or third root of lambda to take into account that this volume and this is diameter. And here we have lambda versus mu. Lambda is volume or K per volume, and mu is magnetic saturation per volume. So they are supposed to be linear. From the correlation, we can obtain information about, in this case, about the effective anisotropy constant, and we can, from the value we obtain, in fact, we obtain the effective anisotropy constant of the magmite because of the construction. But with this easy relation or assumed relation, we obtain the other one. And both are very, very near the ones of literature for nanoparticles. There is some difference if you use to make the correlation, use a line that has a free value, an independent value or not. But both are in the same values. And from lambda versus mu, we can obtain from the slopes the relation of K versus MS, magnetic saturation, that is also near the values of literature, or for bulk value. I have here, when we made this study, we obtained from 0.4 up to, this is strange, I suppose that we have to remove it, but all the other ones are between 0.02 and 0.4, and here are the values for bulk, 0.023 and 0.13. So the values are, the mean value obtained from the correlation is also very well. And here is the correlation between magnetic saturation and the fraction of magnetic like, because I'm not saying that it's magnetite or it's magmite. What I'm saying that it behave or it has a shape that the hyperfine field is, and the distribution is in accordance with sites like the ones of magnetite. And here we see that if more near magnetite, higher the magnetic saturation, and more near magmite, lower, but more distributed. But we have to take into account that here appear how the size of the particles affect the magnetic saturation. So here we have different sizes inside. So, conclusions. We have significant variations in the synthesis, in the 6, I suppose that there were 6 syntheses with different aliquots that were studied in different ways. We see around 12% in dispersion of sizes between different batches. We found a model that allows us to model the spectral curves using a reduced set of parameters. I think that this is important. It's a way to have an identification of the most power pattern with some values. In that case, the values are the lambda, the mean lambdas, each mean lambda, also the whole mean lambda, and the relative fraction between the two contributions. And they are close related to particle size and relative abundance. So one can talk about that is bigger, that is smaller, or that has more magma-like, or that is more magnetar-like. We found that the values obtained from the parameter lambda correlate well with the crystal size and also with the magnetizations of the magnetic moment obtained from magnetization. And we progress because the one that you have seen was not 2 years ago. We progress with the structure in a Python code that can be managed interactively by console, that allows us to fit most power effect spectroscopy, and maybe I can say that it can be fit these nano profiles, but in fact it can fit anyway because the LM fit and the psi p allows you to fit whatever you want if you can code it. Okay. This is the author, and in case you have like more or less what I have told, you can consider that all these people have worked hard to take this here, and in case you more or like don't like, you don't consider these people, only me working. Okay, and thanks for your attention.
Thanks, Gustavo. Time is for question.
Gustavo, very nice presentation. How do you measure the stability of your nanoparticles using zeta potential or dynamic lattice scattering?
they were measured time ago, yes, and they were stable. But this this batch that has a separation, a different separation than the previous one, we separate by centrifugation, and the last one was separated by magnet. We don't have measured the stability, and in fact we see that they are not stable. You can see that they go to the bottom some part of the part with the time.
Thank you.
Not all, but you see a fraction, a small fraction that go to the bottom. So there is some no stabilization.
That's why you try a model of distribution, because you feel that there are two significant distribution of small particles and bigger particles associated with that decantation and stabilization. Because when you prepare the samples by co-precipitation, you see that when you put the imant near to the bottom flags, some particles precipitate easily and others are stable, right? And that's important. You took only the particles that are precipitated with the imant, or what happened with the others that stay?
We precipitate with centrifugation when we wash, and we resuspend in water after that. These samples are this kind of sample. We don't use the supernatant. We model with two log normals or two distribution because it was easier. The other model is the core shell model. It's assumed that you have two phases, but it is not the same. It is another approach. Here we propose two different a mixture of two contributions. A mixture of because they are independent. Maybe you can interpret it, but it's not easy at core shell.
Thank you, Gustavo. Thank you to show us how was the card for computer. At one moment, you have taken into account the values of anisotropy of magnetite and magnemite. So I presume that you have no nanoparticle of magnetite and nanoparticles of magnemite. They are magnetite covered by magnemite. For the contribution of magnemite, did you consider the surface anisotropy, which should contribute to the anisotropy of magnemite?
I understand a little, but maybe you can ask again. Sorry, that part.
So your sample is a mixture of the two phases, or they are only one phase, which means that you have one nanoparticle which is covered a core shell system.
The purpose of the fitting is that it's a mixture, as it's fitted.
Okay.
As it's fitted.
Okay.
You have to, and what we have seen by other techniques, by microscopy that I can not shown, it shows something homogeneous. It's difficult to see core shell by other techniques.
Yes, about the core is of magnetite. You consider the magnetic anisotropy of magnetite. That's right.
This one.
The surface is essentially magnemite. So you consider the anisotropy of magnemite. But did you consider also the surface anisotropy, which is very important?
Okay, because this correlation, this is a way to transform the lambda from one to the other one. For that, I use the bulk parameters. Yeah. The results give us something something that can be interpreted enhanced because surface anisotropy, because it's higher. What we obtain are higher values than bulk values. This was only to transform from what was obtained for magnetite to a magmite, and for that I use the bulk values because at that moment I don't have information about.
Okay.
Yeah. Okay. Yeah. Okay, let's thank all the speakers again.